All right, I need to, let's get going, because I got a lot to cover. Let's get going. Let's get good! So I sent an announcement on Friday. I haven't scoured my email. I'm looking for the rest of the field trip data from the group that has not yet sent it to me. And I take some responsibility for them not having done that because the method that I set up did not work. Because I didn't realize that while I can attach files to discussion items, you can't. So, let me just ask. I did get emails with the data from 2 of the groups, and I need the data from the 3rd group. Has that been sent to me? Can anybody tell me? Yes, awesome. So I will compile that and post that. Try to remember to do that after class today. Because I want to get that back to you, available to you, so that you can then work your whatever magic you figure you can work on it as I ask you to do in the field trip guide. And then field trip reports will be due on Friday rather than today. Hoping everybody got that message. Cool. All right. Another item of logistics. Of course, you guys had a midterm on Friday, and I plan to get that back to you on Wednesday. Okay. I want to then talk a couple of, all right. Last time we talked about landslides, and this, I said, okay, now we need to talk about a couple of things about landslides. Let me just first sort of, as a way to transition, that there are different types of landslides, right? There are rock failures, there are deep-seated rotational landslides, etc. We are focusing on a particular kind, the sort of shallow soil layer failures with the potential to become rapid debris flows. The physics are simple enough to be tractable, as we've dealt with so far, and complex enough to provide the elements that are transferable to other types. To at least help you understand what's going on with some other types, and with some more advanced training, even deal with those. The rapid debris flows also provide us a nice transition point from the hill slope to the channel. We've talked about, okay, we've got this diffusive stuff and we get soil building up, and here we're talking about when it fails. So in order to make that transition, I want to consider 2 questions for a day. One is, where does the water providing that pore pressure, because we talked about pore pressure being a fundamental thing in determining whether we're going to get a landslide failure or not. So where does that pore pressure come from? And 2, will the landslide become a rapid debris flow that typically becomes channelized and typically is the sort that kills people, or will it be a slow earth flow? So I want to deal with that second first. Let's, oh my. All right. So let's talk a bit, and suddenly I start writing in all caps. That's weird. It's just like came naturally. It's like, oh, that's big. Okay. So, let's deal with that first one, or the second one first, the fast or slow. And we might think of this as, well, we've got the go, but is it a go fast or a go slow? And partly what it comes down to is acceleration versus deceleration. And that comes down essentially to liquefaction or not, which is essentially determined by whether the material is loose or compacted at the point when it becomes unstable, or at the time when it becomes unstable. So I want to show you some video from the debris flow flume at the H.J. Andrews Experimental Forest in the Western Cascades. So the first one I'll show you is from a loose bunch of material. If I move that out of the way, it should tell you that the dry bulk density, so this one, loose material, dry bulk density 1.2 grams per cubic centimeter. And let's old 90s video, so kind of low res. So this is Dick Iverson. He's kind of he was the PI for all this. The guy up at the top there is Rick Husen, who's now obscured. He's the instrumentation genius. So they're sprinkling on it with these sprinklers. They've got all sorts of instruments in it, as you can see. And what you might have noticed, and we'll get another one, but what I want you to pay special attention to for the next one is, how long does it look like a sliding solid versus a flowing liquid? I think we will go, here we go. So to my eye, it looks like about a second, maybe not quite a full second, between when it, starts moving, looking like a sliding solid, to when it starts to flow, and the rate really picks up. All right. Let's then look at another. This one, we've got a dry bulk density of 1.56 grams per cubic centimeter. Same material, they just compacted it. And that's important to remember, same stuff. Again, they're just sprinkling on it. I think they're getting impatient, and they're just going to really crank up the sprinklers big time. Notice we just jumped ahead 2 hours.
Potential. They are simply equal to that elevation, which is somewhat less. 73. Oh, it's going, it's going.
Well, some of it,
gravel there, man. Maybe turn off that yellow-green.
Gravel there. We don't want
Craft width is accelerating.
the guy yelling is probably Rick Lacusa. He's watching an old school like computer screen in that shack. He's watching the strain meters and the potentiometer, the head measuring device. Yep. He's telling them it's moving. Right? And they're like, oh cool. And then it stops. No, some of the videos on this site are not there anymore. There are some that are a little more, even more anticlimactic than that, where it just never really gets going. So let's look at what's going on here. So let's consider something I think we can maybe relate to, although maybe me more than you, because I don't know. Everybody knows, like, you know, what coffee cans used to be like. I mean, we don't buy coffee in cans anymore, but you know, your basic coffee cans. So say you've got, let's consider that we have a coffee can, and first we pile stuff in it loosely. So there's our ground surface, as it were. And we put some water in there, filling it part way up. And so we've got our water table there. Okay, now, again, we put it in here really loosely, and then we shake it. So what happens? Well, our initial material surface goes down a bit. Okay, so we've got our material. Yeah, zoots. This is not going to work for me. It started off sharp, and I just blunted it. So our material settles a bit. Our initial water table then, if our material settles, what's happened? Well, the amount of pore space has decreased because we haven't just sort of made some rock volume, some grain volume go away, right? It's pretty much an incompressible solid. We've gotten rid of some pore volume, and so then our water table goes up. Well, what happens when our water table goes up? The pore pressure goes up. Remember, the pore pressure is all about the head. It's not about some mass of water. It's about the level of the water in there. Sophia?
What are the bonds like you don't
So these are just the initial ground surface and water table heights.
Oh,
So the water table's gone up, the material surface, the ground surface has gone down.
okay. After raising
Yeah, we stuck the stuff in there really loosely, then we shook it, the material settled.
it?
We had water in there, we decreased the pore space when we shook it and settled the stuff. And so the water table rises. So let's look at what happens in that sort of situation. So these are data from the debris flow flume. Now, as you might imagine, when a material starts to slide, that agitates it. That's the shaking. And so when you start with an initially loose material, here they're saying the initial porosity is 0.52. We've got time on this axis, but note that we go 0 to 1,000, 2,000, 2780, and then we proceed second by second after that. Up here we've got displacement, here we've got pressure head. So you see initially there's a bit of displacement, or I don't know, let's look over here, this is better. We've got a little bit of displacement, especially over here, and these are pressure head measured at different depths at 67 centimeters, 50, 30, and 10 centimeters depth in the material. And what you see is a rapid rise in the pore pressure as the material is being displaced, and an accelerating displacement. So again, let's think about that. If we start off with our material right at factor of safety equals 1, right? We've got enough water in there for it to just go, but then we settle the material and we jack up our pore pressure. So what's that make happen? That makes our factor of safety drop suddenly and substantially. And now the material isn't just barely moving, now it's really going to start accelerating. That's liquefaction. In effect and in reality, the pore pressure rises to near lithostatic pressure, so that it becomes essentially like a liquid. And that's what we saw, that after about a second of sliding like, or maybe less than a second of sliding like a solid, it starts looking like a fluid. Okay. Now let's consider the alternative case in which we've got a compact material. Again, in a can. Try to draw this approximately.
That's what that second video was, right?
Yeah, so this would be like the second video, where we've got the compacted material. We've got, say, some initial water table in here. And as we saw, if I'm trying to act like this is something that would be like a failing mass, the water table had to be really, really high for that compacted material to fail at all. So let's start with a pretty high water table, and then again, we shake it. We shake the can, that's essentially like making it slide, or sliding it is like shaking the can. And what happens then? Well, these grains are interlocking. They're compacted about as tight as they could be. So in order to shake it, in order for that material to move, it's got to get bigger. It's got to expand. So in this case, our material expands. And our initially high water table, well, if we started off with a small amount of pore space, the material expands. That expansion comes by adding pore volume. And so our water table drops. So in this case, if I was initially at factor of safety equals 1, but then I drop my water table, then my factor of safety is going to abruptly rise. Right? We're going to, high factor of safety means stable. The material then stabilizes. Here again are data from the debris flow flume. Notice that we're looking at a much longer time scale, and even as we get out here, 300-second intervals thereabouts. Yeah. So notice here, okay, we've got a dense soil. It's the same stuff. It's just compacted, so the porosity is lower, 0.41 as opposed to 0.52 was what it was before. And when we get a little slip, what happens to the pore pressure? It drops. And then it gradually builds back up until it slips again, then it drops. And it builds back up until it slips again, and it drops over and over. So now we've got a slow creeper. So, by the way, if you're going to build roads out in the forest somewhere, it'd be really nice of you to compact the heck out of them, because then they're less likely to fail rapidly. But this is, Dick Iverson got a science paper out of this when he finally figured out what the heck was going on. That same material, in one case it's just tossed in there loosely, in the other case it's compacted. In the case where it's tossed in loosely, it fails rapidly, accelerates downslope. In the case where it's put in there compacted, it just inches bit by bit. And we didn't see the precise experiment that this one is, because I couldn't, all the videos weren't available. But in this particular case, you can see that it never really all went. It just went inch by inch, bit by bit, until they gave up on it. Because, federal going home time is 4:30, and they were probably past that time by then. Nah, anything in the name of science, right? So, but it is funny to watch these videos as the time gets up to 4:30, and you're going, oh man, that's quitting time. Harsh. All right. Okay. So to summarize, again, initially loose material with enough pore pressure for a factor of safety equals 1. It slides. That's the shaking of the can. The settling of the solid raises the pore pressure to the point of liquefaction, and we have a fast debris flow. If we have initially compact material with enough pore pressure for factor of safety equals 1, it slides. That's shaking the can. The material expands. The pore pressure drops. And so the material becomes stable again until pore pressure builds up enough again for it to inch a little bit more, and that's a slow earth flow. Do you have a question?
I was just wondering if there was anywhere in between these two loose and compact soils where shaking it wouldn't do anything. Equilibrium between water.
Well, there does appear to be effectively a critical porosity. That is the porosity that it is at when it's rumbling down the slope. So I suppose if your porosity were exactly that initially, then I don't know. I'm not sure what would happen. Maybe it wouldn't accelerate very much, or it would creep not so slowly. I don't know. I mean, it does appear that the degree of compaction does affect, that if I compact it more, it's going to inch more slowly than if I compact it a bit less. But again, I want to emphasize that's the same material in both of those cases. The only difference was whether it was just tossed in there loosely or compacted. And they had actually used a hydraulic kind of thing to, square hammer, basically a jackhammer on a mount that they would move along, go, and they piled the stuff in there. Okay. So that's the first thing I wanted to talk about. We know that it fails, but when it fails, do we need to jump in the truck and drive fast, or do we have time to get the silver and grab the computer as if nowadays, right? Do we have time to grab our stuff, or do we run outside naked? If we have any warning at all. There's a good video, I've linked to it on my YouTube channel of a case in, I guess it was February '96 in Portland, when some contractors were up and a landslide happened, and it's this great video. It's like guys standing in the back of the pickup truck, and they're running away from a debris flow that's pushing along another pickup truck after them, and you can hear the tires squealing on, scraping on the pavement and all that. It's great. Luckily they survived. All right. That's the second thing I wanted to talk about then, was our water source. And in short, our water source is rainfall. And it's rainfall on an upslope. I'm going to write out all these words because this is a concept that will come up again. Upslope contributing area. So that is, we've got some area that is receiving rainfall, and that area, and the rainfall falling on that area flows to our point in question, at which we're trying to do our calculation as to whether we're going to have stability or not. Okay. Now, typically then, differences in contributing area across a landscape largely determine, well, those differences in contributing area, of course, it also has to be really steep, but those differences are largely going to determine the differences in landslide susceptibility across space within that landscape. So this, so let me make it clear again, this plus slope is going to determine our landslide location. Now, imagine you're in Oregon in the Coast Range, and this may be hard to comprehend. It's raining forever. And so, you do have just, background levels of water flowing through the soil, background levels of pore pressure. And then it starts to rain really kind of hard. And so our other source of water is essentially the local rainfall. We can think of it in two senses. Maybe I can sketch this something like this. If this is our ground surface, that, we have water flowing in from upslope, but we've also got rainfall falling directly on the slope. And while the stuff above the water table is not saturated, it's pretty dang close. Essentially zero surface tension here. Pore pressure is 0. That is, we don't have a positive pore pressure. We're not below the water table, but neither do we have any tension, negative pressure holding it together. We hit it with rainfall, and especially if we get a big peak, well, changes in rainfall are largely going to determine the differences in landslide susceptibility across time. So this local rainfall is going to give us the time of failure. That is, all else being cooperative if we're wanting a failure in the first place. Cooperative, wanting, that is, we'd also need it to be steep enough. We need to have the contributing area. We need to have low enough root strength and so on. But that spike in rainfall, should we get it, is largely what's going to determine when we get the failure. Let's look at some more data. On a site here in East Bay called Metman Ridge. Here's a LiDAR DEM of the general area. Here is a close-up then, both with contours and the LiDAR hillshade, and I've flipped it over so north is now pointing down, and I negative the image so that it should still look like a landscape that is not inverted. Okay. This thick outline is what's outlining landslides and the runout track that have occurred at this site during the time that it was under study. And the location of that scarp there is right about there. Now, one thing we can do is simply look at that and go, yeah, there are places in the landscape that are convergent. There are other places that are divergent, and those are gonna correspond to places where the flow, where we've got concentrated versus dispersed flow in the shallow subsurface. So the water that's flowing, say, over the bedrock beneath the within the shallow soil layer, is going to, of course, gather in these indented convergent parts of the landscape. So those convergent parts are where contributing area is, of course, larger. And then, of course, the further downstream we get along those convergent parts, the greater the contributing area. Now the landslides then occurred at locations of convergence and steepness, right? Pretty close to the divide up here. So again, the steepness part is pretty important. And the landslide here at what's labeled CB1 also appeared to be assisted by the fact of this road. That there was some flow off of the road diverted onto the slope that made, boosted the effective contributing area of that spot. Okay. Here, this is maybe a bit much, but here are some contours, again, zooming in on that headscarp part of the site in CB1. And the black are elevation contours, the blue are water table contours. So, at the risk of being a completely confusing plot, you can see at least that in these areas where the landscape is more convergent, where these contours are more curvy, we've got higher water table. Over here, for reference, is the start of the actual landslide. And I've tried to kind of line these up so that they're about right, about even. Here's the 280 meter contour, I think, and again 280 here as well. This is a calculation of here's where factor of safety equals 1 according to whatever model they were doing that calculation with. And that corresponds to about where, we start necking narrow in this, from down the slope of this headscarp. In my experience, it tends to be true that, so you remember in the flume, they were showing these failures and they had to have them ramp up over a barrier. You will often actually, especially if you get to a landslide site not too long after it failed, you'll often find a bit of a lip on the ground before the landslide debris flow gets going fast enough to where it's scouring out everything down the slope. Okay. Now here is precipitation intensity here and discharge at these weirs. So an upper weir and a lower weir. They put in the lower weir because they realized that the upper weir was missing some water that was going through an exfoliation fracture in the rock, and so they were missing it. And here is November 1996, and you see the spike in rainfall, you see the spike in the precipitation, and then the precipitation record ends. And that's because it ended violently. Just show you, try to line those up a little better, or illustrate here just how close upon the spike in rainfall the spike in precipitation occurred. That essentially means, okay, that's got to be the local rainfall. That's a pressure wave that's moving much faster than, well, way faster than any sort of flow velocity of the actual water through here. The pressure is transmitted relatively rapidly. It's also essentially too fast for that pressure wave to be transmitted from upslope. It really had to be transmitted down through the soil column by that that soil layer that is very close to saturation, and then we hit it with a bunch more rainfall intensity, and that spikes the pore pressure enough for it to fail. So, summarize that. Again, the contributing area tells us the where and the slope. The contributing area and the slope are telling us, where is it more wet, and of course, where is it steep enough. But that precipitation intensity, and also just, that kind of intensity after, this is a good day long, pretty heavy rainfall before it really spiked up. That timing of that spike is determining the timing of the landslide. So that's why you might want to develop, or you will sometimes see people develop curves something like this, where I've got on this axis mean rainfall intensity, inches per hour, rainfall versus rainfall duration in hours, and I've plotted up events when there have been landslides. This is for the Seattle area. And so, we develop, based on those data, an envelope that says, okay, as long as our intensity and duration are below this curve, then we shouldn't be worried too much, but as we get closer and closer to this curve in terms of our intensity and duration, we start to get increasingly alarmed about whether there might be a landslide. This curve again isn't going to tell us exactly where we're going to get a landslide, but it's telling us that, okay, based on other landslides that have occurred, be mindful of those places that are susceptible to failure based on their slopes and their contributing areas and so on, and watch out for failure. Yeah?
Purple diamond is random times, right? Not specific time of landslide?
Oh, right. Well, I think essentially what we're seeing is that these are a couple of times when there were a bunch of landslides, and then the purple diamonds are just every other landslide occurrence they could find. Because again, you want to, it's likely that those events during which a lot occurred, the rainfall in that event was potentially a lot more than you needed to trigger that first landslide. So they're really looking for that lower envelope, trying to gather all the information they can from even the events where there weren't a bunch of them, maybe just one.
January 86 is kind of late, it's a lot of rainfall.
Yeah, a lot of rainfall. It is interesting to look at some of these durations, or some of these intensities. Because we're looking at inches per hour. By southeastern U.S. standards, these are really wimpy little rainfalls. But that's why in southeastern U.S. you don't get landslides. You get flash floods. Here in the Northwest, it just gets steeper, got that tectonic convergence, just making things steeper and steeper and steeper until it gets waterlogged one day and just gives away and fails. So it is kind of peculiar to our climate and our tectonic environment here that gives us that susceptibility to fail. Of course, in Seattle, you've also got the issue of all that old glacial material is sort of sitting around in big stacks, unconsolidated here and there. And then people like, out on these islands and the Sound, people like to build their houses in places, and then people get killed, and then people forget, and people build a new house in the same spot. Tragic and sad and easily sometimes. Any other questions? I was convinced I was just going to have to rush through this, so I'm afraid I did kind of rush through, but I feel bad. Yeah.
I do have a question. How did they measure the discharge on the last graph from the weirs if the weirs got destroyed?
So they had, I don't know exactly what kind of instrument they had, maybe a pressure transducer, and these were steel weirs, so they had them calibrated. But then they were logging the data via cable to instruments in a shack. And luckily they actually had stuff recording. I don't know that they had everything recording or everything going, but they had a lot of stuff actually running. Their plan, they had actually planned and got, this is Weyerhaeuser land, and they'd actually gotten permission to purposefully kick off a debris flow. They had gotten permission to just try to rain the heck out of it with their sprinklers until it failed. And, you know, sort of study a field scale landslide under controlled, somewhat controlled conditions. But then the November '96 storm happened and took their experiment away from them. But luckily, at least they were recording discharge, they were recording, at least had some of their piezometers recording levels and being recorded in the shack. I meant to, but in that time, put some photos in here. Essentially, you know, they I'm pretty sure rushed to the site after that storm because there were landslides all over the coast range and everybody knew that. And when they got there, of course, you know, they come and they see this scarf with their cables hanging over the edge of it, and all their nice catwalks, you know, either just gone. I mean, a lot of stuff was just gone and never seen again because it ended up in, you know, down here somewhere, buried under however many meters of material.
Do you know how big of a landslide it was? Like how much material?
Not off the top of my head, no. And I don't know exactly how much it ended up. I mean, what you see here is a bit misleading in the sense that you see two scarps and they're sort of tied together down to this deposit here. But this one occurred several years before this one. This one actually occurred on the same day that the co-author of our textbook, Suzanne Anderson, had, earlier the day it failed, she had been at the weir below here gathering waters for doing water chemistry stuff. And later that day it failed. They had a great safety scheme here. You know, so they had catwalks all along this nose here, and actually kind of crossing here. And they had this steel cable that sort of went diagonally across the site and terminated somewhere on this ridge. The idea was that nobody should be out there without thick leather gloves on, and if something started moving, grab the friggin' cable and hold on for dear life, and literally, and then, you know, hopefully slide on the cable down to the ridge. I mean, that passed Weyerhaeuser muster, I guess. Weyerhaeuser was like, you got to have something. So, all right. So next time we will go on to talk more about water in the landscape. Then I will get those survey and Gopher Mountain data compiled and posted for you today. And get exams back to you on Wednesday.
The lab report, the field trip report is just the packet.
Yes, yes. So it asks you, we take these data, make these graphs, and I just wanted to give you all the data so you can make graphs.
Oh yeah, and we don't have to do the questions for the last stops that we missed.
What's that?
We don't have to do the questions for the last stops that we missed.
That's right.